Before we get into anything, if you'd like to follow along on your own screen, I know it's hard to see this from the back or even maybe from the front sometimes, you can go to this shortened link and you can watch what's on the projector in real time. Okay, a little introduction about me. This is my second year this is my second time at the Tcl conference and my second time giving a talk, so thanks for having me back. Joke's on you. For the last 3.5 years, I've worked full-time as a developer at FlightAware. For most of that time, I've worked on Hyperfeed. It's the core flight tracking engine that takes as input a stream of dozens of data feeds and outputs a canonical representation of FlightAware's understanding of global flight activity. Recently, I've been focused on distributing Hyperfeed and in conjunction with that, increasing its availability and reliability. When I first started working on Hyperfeed, it was highly parallelized, but it only ran on a single machine. And if that machine went down, we didn't have a straightforward way of switching over to another machine. Of course, it could be done, but it would have been very painful. So I've been working recently on fixing that situation, and my talk is based on this work. I'm not going to go into the details or the inner workings of Hyperfeed. If you're interested in that, Google the 2016 proceedings. My colleague Zach Kahn wrote a great paper on that topic. Instead, I'm going to be speaking at a higher level of abstraction, just talking about coordinating the different components in Hyperfeed or in a system in general that looks kind of like what Hyperfeed is like. And to accomplish that, I'm going to be demonstrating the use of Zookeeper for doing this. Zookeeper, I'll get into the details, but it provides a very simple API that's a little mysterious when you first learn about it for achieving coordination in distributed systems. When I first learned the API, it wasn't clear to me how you could use it for actually accomplishing anything useful, but the official project provides some recipes for accomplishing common tasks in distributed systems. And the system that I'm going to be demonstrating is based around one of those recipes. But one of those recipes, or the recipes in general, are very generic. They just show how to use the API. But if you're actually implementing the system, there's a lot of decisions and a lot of things that come up that aren't covered in the recipe. So I'll be discussing those at the end after we get through all the intro material. All right, so the system itself. This is how I'm reorganizing Hyperfeed, but any system that follows this, and hopefully this is general enough to cover a lot more systems other than just Hyperfeed. So in this system, we have multiple processes or multiple components. I'll be using those terms interchangeably. A component in the system could consist of multiple processes, but logically you can think of them as the same thing. And all of these components need to be running concurrently. They need to be running at the same time, but there's too many to run on a single machine, hence the use of a distributed system. So in the system, we have multiple nodes. Unlike human society, this is an egalitarian system. All the nodes are created equally, both in terms of compute resources and in terms of their ability to execute or to run one of these components. There's a bit of a limitation on each component. So each component needs to run on one and only one machine at a given time, but a single node can run multiple components. Okay. This is not a utopian system, even though it's egalitarian. Faults and failures can happen. I'm going to be using the terms fault and failure pretty interchangeably as synonyms, although maybe in distributed system or other literature, there is a distinction to be made, but forget about that for now. So we're going to expect both temporary and perhaps permanent failures of both the components themselves and the machines that are running. So we want to tolerate two general classes of failures. We want to tolerate when something crashes. This is typically a hardware failure. We also want to tolerate an emission failure, meaning one of the components fails to give a response in some amount of time. You can think of this really as a network failure, a network glitch that prevents it from actually sending out a response or doing the work it's supposed to be doing. Just for the people that have heard of this, if you haven't, just tune out if you weren't already. There is a famous result in distributed systems known as the CAP theorem. The CAP theorem is an acronym. It stands for consistency, availability, and partition. And it says, in summary, that you can only really achieve 2 out of the 3. So this system, we're just going for A and P. Okay. Since we expect failures to occur, when they do occur to a single component, we want it to run on another node. And if a particular node fails, we want all of its components to run somewhere else. So the system I want is one that has many components that run across multiple nodes and can support automated failover for the common failure conditions that I mentioned in the previous slide. Confession time. We can't protect against all failures, sorry. In particular, the consistency or integrity faults are unaddressed by what I'll be mentioning here. Also, there's a class of failure that's known in the literature called Byzantine failure, and these are arbitrary failures that are introduced into your machine or into your system at arbitrary points in time, either because of a bug or because of malicious components that are trying to ruin your life. We can't prevent those, unfortunately, sorry. And then the dealing with emission failures, the network partition that I mentioned, there are some caveats to that. There's only a partial addressing of them. There are some cases where it won't be addressed perfectly, just based on what I'm going to be talking about today. Okay, so to achieve all of what I've just said, we're going to use Tcl, and in particular, we're going to interact with Zookeeper through Tcl. And we're going to use the leader election recipe, but I'm using the term leader election in somewhat of a peculiar way. Typically, if you hear about leader election, it's in the context of consensus, like Raft or the atomic broadcast protocol that Zookeeper itself uses, or in something like Kafka, where you have multiple components, they're all trying to achieve a common end, and one of those components is a leader, and the rest are followers, but they're all participating in this particular computational task at the same time. In this system, a leader is just whatever node is running a particular component at a time. Okay, so each component is going to have a leader, and that's who's running the component, but the other nodes are ready to step in at any time. So the other nodes are greedy for power and leadership as well, so whenever they get a chance, they're going to step up to the plate. All right. On each node, so to implement this system, we'll need to create a supervisor process. I'm not going to detail the code for that. You can just imagine how this might work. So the supervisor is going to communicate with Zookeeper. It's going to perform leader election. At its most basic, it'll run a loop for each component in the list of components, perform leader election. And if you win the election, run the component. And if not, watch for the other leader, or the node that did win the leadership, to die. Also, so it's a supervisor in the sense that when it does win leadership of a component and runs it, it will monitor this component in some method. Sigchild is an easy way to do this. So that if the component dies on that node, but the node itself or the supervisor is still up, it can delete any state that's in Zookeeper that signifies that it was the leader, and allow another machine to take over. So the supervisor then needs to know how to start and stop each component, and it also will know all the other nodes that are in the system. All right, let's talk a little bit about the Zookeeper. Just to show of hands, how many people have ever heard of Zookeeper? Use Zookeeper? Much smaller amount. Perfect. Okay. So Zookeeper is a distributed coordination service. A lot of buzzwords. You'll see what that means a little bit. It was originally developed at Yahoo, but it's maintained by the Apache Software Foundation these days. All of the code is in GitHub. It's written in Java. Sorry. You can run it in two main ways. One is really just for development or testing. This is with a single Zookeeper server. But the real benefit in the way that anybody really wants to run Zookeeper is replicated, meaning you have multiple machines that are running Zookeeper. And if you have 2K plus 1 servers, you can handle K failures. So if you have 3 servers, you can handle 1 failure. 5 servers, you can handle 2 servers going down, etc. Okay, so it's a distributed coordination service. What do we mean by coordination? So there's a lot of tasks in distributed systems that reoccur over and over again, and they're pretty difficult to get right, particularly because of deadlocks and race conditions. And if you've ever done any thread programming with semaphores, you know what I'm talking about. So some examples of coordination that you might need to do in a distributed system. There's something known as a barrier. So a barrier is a way for asynchronous threads or asynchronous processes to act temporarily in a synchronous fashion. So they reach this barrier, and once all of them have reached this barrier, they can all proceed. Distributed queues are another common use case of coordination. Locks are very common when there's a shared resource among machines that maybe you want to prevent only one process from writing to it at a time, or one or several processes from reading it, but no more than that. Two-phase commit, this is a way of getting transactions among many machines, where they'll either commit all of a particular transaction or do none of it. And then leader election, as we'll go through. Okay, so Zookeeper itself doesn't come with an implementation for all of the tasks that I just listed. Instead, it provides a very simple API that makes it a bit more flexible. You use the API to then implement the coordination tasks and to get something done in a distributed system. And the hope of the Zookeeper project is that because these coordination tasks keep reoccurring in distributed systems, if they can get it right in this one library or this one service, then everybody can depend on it, and it offers a lot of nice consistency and availability guarantees. So if you need to accomplish any of this coordination, you can just rely on Zookeeper and assume that it works right. Okay. So the API is based on a file system-like abstraction. The main data structure, or the only real data structure, is known as a znode. A znode is a combination of a file and a directory. Every znode exists in a hierarchical namespace, starting at a root, which is just a / like a Unix file system. Znodes themselves are like files in that they can contain data, but the data they contain is typically a small amount, about a meg. You can configure it to be more, but it's not meant to be a large data store. But they can also contain metadata, and they do contain metadata. But they're also like directories in that they can contain children of themselves. So they can contain znodes that are children of them. Okay, so the system that we're working with looks something like this. We start with a root znode, just a / in the namespace. And then each component has its own znode. They'll be named after the component. And then there'll be two main branches that go off of that. One is a configuration branch, and that contains all the data that the supervisor running needs to know to run that component. So you could store all the arguments that you would need to run the component as data in that znode, or you could have separate children underneath the config where each child znode's name represented the option that you wanted to pass in the command line to run it, and the data in that znode would be the value for that option. And then in addition, we also have an election znode underneath the component, and the children under there, which will exist, are all used for leader election, for figuring out which node in the system is going to run that component at any time. So the API operations, pretty simple. You can create new znodes. When you create a new one, they can either be durable, meaning you can create it, you can disconnect from Zookeeper and it will still exist, or they can be ephemeral. So they would only exist, in that case, for the lifetime of your session to Zookeeper. So if you create an ephemeral znode and you disconnect, it won't be there when you come back. In addition, when you create a znode, you can add a monotonically increasing integer to the end of the name, to the end of the path that you're creating. In the leader election recipe, we use both of those, so it's possible to create an ephemeral and a sequential znode, or a durable and a sequential znode. You can delete existing znodes, you can query them, you can ask whether a particular path exists in the namespace, and you can also ask for a list of the children of a particular znode. And then you can get the data for a particular znode, or you can modify the data that's there. Something very nice that Zookeeper offers are watch callbacks. You can set a watch on a znode when you're querying it, when you're asking whether one exists, or you're getting the data for it, or if you're getting the children for a znode. And these become one-time callbacks, meaning you have to reset them each time it gets called, but they will be invoked whenever the znode changes. So if you set a watch on a get or exist operation, if the znode is modified in some way, either it gets created, it gets deleted, or the data gets modified, your watch callback will get invoked. And then the other watch you can set is on the children. So if a child dies or a new child is added, the child watch will get called. All right, so it's been almost 20 minutes and I haven't said anything about Tcl, so here we go. In order to use the Zookeeper in Tcl, you can use the Zookeeper-Tcl library. Thank you to Carl and Shannon who have worked on this. It's all open source, anybody can use it and unlock the power of Zookeeper in your Tcl programs. So the Zookeeper project itself comes with two official clients, a Java client, naturally since it's written in Java, and a C client. The Tcl library wraps the C client. And it really supports up to the latest stable Zookeeper version. There's some additional features like TLS that are coming out in further releases that aren't supported yet. A nice thing about the wrapper is that every API operation allows you to invoke it synchronously or asynchronously, where you get a callback whenever the operation completes. So depending on the needs of your program, you can use either style. All right, some code finally. Looks like I'll just from up here, so you probably can see it. If you need the link again, it's bit.ly/tcl_zk. Talk through this briefly. To use the library, you package require Zookeeper, as you might expect. One sort of annoying thing about the C client, at least annoying to me, is that it outputs a lot of debugging statements to standard error by default, but you can turn that off by setting it to none. And for making a connection to Zookeeper, there's an init command, and the the init subcommand of the zookeeper command takes 3 required arguments. One is the name of a zookeeper command that you're going to be creating. So when you actually connect to Zookeeper, you get back the name of a command that you can then use to call subcommands on for using the API. It also takes the host string. When you're connecting to a cluster, you do host :port and comma host :port for all the machines in the cluster. And then there's a millisecond timeout. And here's an example of some more just creating things. It's as simple as you might hope. Simple API, simple usage of the library. So this is just a loop that creates a bunch of Z nodes. There exists, query the children, you can get the data, you can set the data, or you can delete something. Now on to the leader election recipe. So the way this works is to kick off leader election, you pick a particular znode path that you're going to create essentially votes, which will be these sequential and ephemeral znodes underneath the starting point. So in code, looks a bit like this. We start with a root path. And we set the name that we want to use for our vote. And we create it by passing -ephemeral and -sequence. So step 1 already finished. Okay. Step 2, you need to then get the children of this Z node. And then we'll let I be the sequence number of Z, which is the vote that we made in the previous step. So we get the children. Okay. And when you create a sequential Z node, the monotonically increasing integer that appends to the end of the path is actually a 10-digit integer that's padded with zeros. So in order to just get the integer portion, I use scan here. Okay. After you've grabbed the children in step 2, if you were the one who created the lowest sequence number or had the vote with the lowest sequence number, you were the leader. So if you're the one with the lowest sequence number, it's pretty easy, then you run the component. If you're not the leader, then you need to watch for the death of the leader. In a naive implementation, everybody would just watch the leader. But this incurs something called the herd effect, where when the leader dies, if you have a lot of potential nodes in your system, it could generate a ton of traffic. And only one of those votes is actually going to step up as the leader, so it's very efficient. So instead of watching the leader, if you're not the leader, if you didn't win the election, you just watch for changes on node J, where J is the largest sequence number, less than your sequence number, meaning it comes just before yours in the sorted list. So doing that is pretty simple. You start off by grabbing all of the children and just pulling out the numbers, pulling out the sequence numbers, and then we can sort those and call this proc called watch next node. And you can just search for the sequence number of your vote, and if it's 0, then you're the leader. That's easy. But if not, you just go 1 before your index in the list, and you know which node to watch. And if that node dies and it was the leader, then you take over from where it is. If that node dies but it wasn't the leader, then you start watching the next node up. So now we have a system that's able to run multiple components in a distributed fashion and to accomplish some sort of automatic failover if some of those components die. And that's just by simply implementing this leader election recipe from Zookeeper. However, just doing that is not enough. There's a lot of issues that you would run into if that was all that you did. So I'll go through a few of the issues that are specific to implementing the system and that aren't covered by the recipe itself. In some cases, you want to give up leadership even though you win leadership. This is something I have called abdication. So imagine that one of your nodes goes down and its components get taken over by another node. So you're running in a somewhat of a degraded state for a little while. Maybe you have to go and replace some of the hardware in the failed machine. And then once you do that and you bring that machine back up, you probably want it to start taking over the work that it once had, so that the load can be distributed a bit more evenly throughout the system. So that would be an instance where you would want to abdicate leadership and allow that node to resume running some of the components in the system. So the way that I implemented this in the system is that if you win leadership, you set a child watch on the election node for that component. When it fires, you then have to make a decision about whether or not you want to give up leadership, whether you want to abdicate leadership or not. The simplest way, I think, maybe making that decision would just be based on fair distribution. You just take the total number of components in your system, you divide it by the number of nodes, use a floor, round up, and then decide if you've achieved fair distribution or not. And if you have not, go ahead and abdicate the leadership of that node and let the person who just voted take over. Well, abdication is a nice thing. It can, in a system that's going haywire a little bit, and in a system that has intermittent failures, it can be actually quite a problem. You can end up with these sort of restart loops. So imagine that you're having intermittent failures on one of your machines. It goes down temporarily for a little while, it loses leadership, its components get taken over elsewhere. Then it comes back up, it runs election again, and whoever has taken over what it was previously running decides, okay, I'm going to abdicate leadership. So this, the machine that failed takes over the components again, but then it goes down again. And you can just keep cycling the components between these machines. So this is something that needs to be watched out for. The way you do this really is by maintaining state. You just need to keep track of when and how many restarts for this component have occurred and on which machines. So then you can factor that into your abdication decision. If the leader of a component realizes that a machine has had a bad track record of running something and continually is failing, you can just decide to ignore it and not allow it to take over leadership. Something else that's not part of the recipe that's pretty straightforward is that oftentimes you want to intentionally stop or restart some of your components without giving up leadership. And there is a performance impact to undergoing leader election. In the case of, say, a code upgrade, you just want to upgrade the code, restart the components, but maintain leadership. So that's something that you definitely want to do, and that's sort of the main justification for using a supervisor process. You could build leadership into every component in your system, but it makes it somewhat difficult to intentionally stop and restart them, because when you stop, they'll lose their connection to Zookeeper, and leader election occurs again. So a simple way of implementing intentional stops and restarts is just by adding special Z nodes that the leader actually will check that indicate you should restart the component, you should stop the component. Something else that comes into play is when you want to change the configuration for a component. Maybe you want to change just one of the options that you use to start the component, and you want to restart it after you do that, but you don't want to give up leadership. So in order to implement that, you set watch callbacks on the config portion of the component's Z node, and watch for that if you're the leader. And one last thing, I'm going over time, apologize, is connection loss. You need to decide for any system that's based on Zookeeper really what to do when you lose a connection to Zookeeper. pretty simple in this case. You want to give up leadership if you really lose the connection, but there are some subtleties here that you can find in the documentation. There are several different states that go into a Zookeeper session or connection. And it's possible that in a clustered session, you would lose your connection to one of the servers, and then you get migrated over to one of the other ones, but you wouldn't completely lose your session. So in a case like that, you don't want to stop the component. You just want to wait and see if you actually regain the connection. And that's it. No questions? Great. Yes. I've outsourced my question answer. No, go ahead.
I wasn't clear if you could dynamically add capacity, like adding nodes to
Yes.
out about failure and that sort of thing.
Yes.
And can you spin up new nodes and let the network know about the nodes so they can join through?
Yes, absolutely. Yes, absolutely. I didn't picture it, but that is something that is in the system itself. There's a list of worker nodes that are available in the system, and that's being watched. So if a node currently running has its entry deleted from that list, so it has its znode deleted from the worker znode as a child, then it will give up leadership of everything. If a new machine is added, then it just becomes a new machine as part of the application decision. So when that new machine comes up and runs leader election, the other machines will know about it and can give up any of the components they're running just for a little. Thank you.